right, so last time we were talking about solving polynomial functions by factoring using the binomial factoring patterns, right? Okay, and why don't you guys go ahead, once you close the Chromebooks up, just maybe not even all the way, but just so you don't get distracted, close those things up. I want to get everybody up here, please. Today we're going to go one step further with that. We're going to look at some other types of polynomial equations bigger than quadratics that we can solve using some other techniques. Okay, so here are sum and difference patterns we talked about last time. We're going to take a look at factoring polynomials with quadratic forms first. Okay, and this is one that really, this is a pattern. This fits the difference of squares pattern, right? But I put this in this section because the difference of squares pattern is a quadratic pattern, okay? It's one that we did, all the stuff that we did in Unit 4, we're going to try to apply some of those patterns to bigger polynomials. How would we solve this one? How would we break this one apart? What did we get here? Okay, so it's x to the fourth minus 2 to the fourth, but we don't have a pattern for a difference of fourths, right? That's not one of our patterns. What pattern would this fit? Wouldn't fit a difference of cubes, would it? X cubed is not compatible with, we can't really write x cubed conveniently at all as, or x to the fourth conveniently as something cubed. But what pattern would this fit? Okay, this could be a difference of squares, couldn't it? Right? So this one, we could write this as x squared minus 4 squared, right? Okay, and then now we can use our difference of squares pattern. So what's that going to give me? Adelaide, what's that going to give me? Okay, times what? Plus 4. There you go. X squared plus 4. Good. And all that's equal to 0, right? Okay. So we could, now what? Where do we go from here? Okay, good. So we got this stuff factored, right? Now we want to find the zeros of those factors. Remember, and this is really important, remember last time we met, we talked about how if I had like a difference of cubes, like if I had x cubed minus 8, I did not have the ability there if I want to find all the zeros, and let's assume we're trying to find all complex zeros. Recall that if it's an nth degree polynomial, then it has exactly n complex zeros, right? So we got to find all those. Some of them might have i's in them. Last time, we couldn't just, if I had x cubed minus 8, I couldn't just isolate the x. If I just isolated the x, I only got the one real zero. I did not get the imaginary zeros, right? So I had to use that difference of cubes factoring pattern. I had to use this pattern right here, or this pattern if it's a sum of cubes. So I could not only get my real zero, but when I have this quadratic piece of my cube patterns, remember this is an irreducible quadratic, it's always going to give me two complex conjugate imaginary zeros. So in order to get all the zeros, I had to factor it. But we didn't have to do that in Unit 4, right? Up through Unit 4, we were always able to solve by isolating. Okay, so the point of this is quadratic, right? This factor is quadratic, so I do not have to I don't have to factor that any further. Once I get it down to quadratic factors, factoring is optional. I could just set those equal to 0 and find all the complex zeros of that quadratic equation that I get. I don't have to factor any further. Like this one, for example, if I set that equal to 0, I just get x squared equals 4, right? And I solve that by square rooting both sides, and I get x equals plus or minus 2. There's 2 real zeros. Okay, how many total zeros, complex zeros, should I get for this equation? Should get 4. Okay, there's 2 of them. What about this guy here? I could do the same thing. I could set this equal to 0 and solve, so I just get x squared equals minus 4. I can just isolate the x there. If I square root both sides, what am I going to get? 2i. Good. I get an I there because I'm square rooting a negative, right? But I got them all. I didn't have to factor anything. I got them all just by isolating x, right? I can do that with quadratics. Okay, everybody, give me thumbs up, thumbs down, thumbs sideways on that. Is that all making sense? Okay, we good with that? All right. Okay, what about this one? What should I do here? What's the first thing I should do? What do you think? Yes, ma'am. Say it again. Move the 2 over. You said, yeah, good. Well, set it equal to 0. Good. We're going to put it in standard form. There we go. So if I subtract 2 from both sides, I'm going to get x to the 4th minus 7x squared minus 18 equals 0. It's in standard form, right? So now what? I mean, this is a 4th degree polynomial. We don't know how to factor a 4th degree polynomial, right? Or do we? This is a trinomial, right? We have a lot of practice with trinomials. This would have been a lot easier if it hadn't been 4th degree, right? Like last unit, this would have been a piece of cake. We would have said something like, instead of x's, let's take z's. What if we had something like z squared minus 7z minus 18 equals 0? So similar problem, only instead of, it's quadratic instead of quartic. Well, that's easy to solve, right? A is equal to 1 and magic numbers exist, right? So what would those magic numbers be? Careful. Negative 9, positive 2, right? They got to multiply to negative 18 and add to negative 7. So negative 9 and positive 2. And then we got it, right? Then we got either z equals 9 or z equals negative 2. That was easy, right? This one seems a lot harder. Is it though? Could we do it the same way? Does anybody see a way we could rewrite this quartic polynomial in a way that we could use the same pattern? It is. You're right. How'd you get that? That's really good. How'd you get that? Into x squared. You see, good. See the idea? That's very good. Okay, we could just organize this in packets of x squared, right? That's the same thing as saying essentially, let's do what we did down here, but let's just make the substitution z equals x squared, right? Everybody see that? And then it's the same problem, isn't it? If I plugged in x squareds for all the z's down here, it becomes that, doesn't it? Everybody see that? So like our arrow goes like this, right? If we make that substitution. Okay, and then look what that looks like. So I still end up with something squared minus 7 times something minus 18 equals 0. And as long as those are the same somethings, that's quadratic, isn't it? Right? It just so happens that the something in this case is an x squared. Okay? But it still factors the same way, doesn't it? Right? So now we end up with the factors x squared, magic numbers are the same, x squared minus 9 and x squared plus 2, right? Isn't that cool? Okay, so we're always looking for that kind of thing. Can we exploit what we know about quadratic factoring, about trinomials, for bigger polynomials, can we reorganize them in ways where we can see them as being quadratic, okay? And then if we just finish this one up, well, you guys tell me, what are the solutions here? What are the solutions of that? What are the zeros of that factor? If I set it equal to 0 and solve, what am I going to get? Okay, good. So we get plus or minus 3. So there's 2 real solutions, right? Or plus or minus 2i, right? Okay. And is that consistent? Here's the graph. Does that make sense? Yeah, matches, doesn't it? How many real zeros are there in this function? 2, and we got them. There's other imaginary zeros don't show up as x-intercepts, do they? Okay. What do they do to the graph? They just make it a little more complicated, right? So it's not just a parabola. It's not like we just got 2 plain zeros. We got 2 zeros and some other action going on here on this thing caused by these other imaginary zeros. Yes, ma'am. Oh, whoops. It's not 2. You're right. Thank you. It's the square root of 2. That's what I wanted. There we go. Thanks. Okay. And look at the last example. I guess I didn't have a graph for that one, did I? Nope. That's all right. Okay, let's try another one. How about this guy? What should I do? First step definitely is what? Equal to 0. So we'll add 8 to both sides. Add 8, so I get minus 8 equals 0. Okay, now everybody stare at that for a second there. What do you think? Do we see a way that we could write this in a quadratic form? Dawson, do you see a trick there? How I could make that quadratic? Oh, okay, so it'd be x cubed would be the packets that it's gonna look quadratic in pieces of x cubed, isn't it? Right? Okay, good. So we could do there. That looks good, right? Now it's quadratic. Do magic numbers exist here? Yeah, they do, don't they? Magic numbers exist, so we can break up this trinomial using a quadratic pattern, right? Magic numbers, and we get those have got to be x cubes. What are my magic numbers here? Okay, -8, +1. Good. Okay. All right, can I just set those equal to 0 and isolate x? So to find the solutions, I've got to find the zeros of those factors, right? So I've got x cubed minus 8 equals 0. Can I just add 8 and cube root it? What's the problem with that? How many total roots or zeros, complex zeros, do I need to get out of this? 6, right? If I just isolate the x, I'm only getting out 1 real, right? That's not enough. What do I have to do here? I can't just isolate. I've got to factor, right? I've got to break this into more factors. Again, because it's not quadratic, I can't just isolate. Can't just isolate x. Okay, so we need to factor that a little bit further. Well, that's just a difference of cubes pattern, right? The 8 is the same thing as 2 cubed. So I should be able to split this thing up then using that pattern, right? It's like my a cubed minus b cubed, where a is x and b is 2, right? So let's see if we can remember those patterns. Remember here's how I do it always. Remember, what I would say is the linear one is going to involve an a and a b. Those are the two terms. In the irreducible quadratic factor, I'm going to get an a squared. An ab, well, that would be x times 2, or 2b squared. So a 2 squared is 4. Now, what's my sign pattern here? What should the sign be here? Negative, and then plus, and then always end with plus. Okay, good. And then we'll do the same thing here, right? This is the same as 1 cubed. So I'm going to get the same deal, only opposite signs this time, right? I'm going to get x plus 1 times x squared minus 1 times x plus 1 squared. And all of that is equal to 0. Okay, now that's going to work, isn't it? How many and what type of zeros am I getting from this factor? Getting 1, what kind? Real. 1 real, right? How many and what type from this one? 2 imaginary. Always, remember, you always get imaginary from the quadratic part of the sum and difference of cubes patterns. Those are always going to give you imaginaries. Okay, in fact, let's put that in the notes. Okay? Every time we're getting 2 complex conjugate roots out of those with i's, right? Okay. So then, same deal here. I'm going to get 1 real, agreed, and then 2 complex conjugates for a total of 6. I don't think I'm going to finish. I mean, we've done plenty of examples like that last time. I don't think I won't drag you through another example. If I set those equal to 0, obviously I get 2 and negative 1. I would just have to use quadratic formula on those, right? And that's going to give me both of my complex conjugate zeros. Are we good with that? If I set those, do we need to go through one of those? I don't think we do. If you need to look at another one, go back and look at the video on that. There's, we went through several examples like that last time. And look at the graph. It fits. See, we've got real zeros at negative 1 and 2, and that's it. And then we got a bunch of other weird stuff going on caused by all these other imaginary zeros. They don't show up as x-intercepts, though. I wanted to do, where did that show up? Man, I had one more on here. What happened? Oh, there it is. Oh, I know what happened. It got stuck in the wrong spot. Here, I want to do this one too, but let me change. I want to put it on this just for the notes so they're organized. I want to move this one page forward. There we go. Okay, what about that one? Same kind of thing, right? I could make this quadratic in pieces of x squared, right? The way we'd say that in math is it's quadratic in x squared. Okay, so we'd end up with then x squared squared minus x squared to the 1 minus 8 equals 0. Okay, that one doesn't factor though. So how could I get answers? How could I get solutions here? It's quadratic, right? It's quadratic in x squared, so we should be able to go back and think about this exactly like we did in Unit 4 until we get a little further in the problem, right? But right now we're just trying to solve this for x squared, and then we'll have to go a step further. So think how you would have done this if those weren't x squareds. What would you have done? How would you have solved that quadratic? Yeah, quadratic formula, right? Doesn't factor, so we'll just go to the quadratic formula. Well, that's fine. We can do the quadratic formula. What are the coefficients here? Well, a is 1, b is -1, c is -8, right? So when we use the quadratic formula, we just get negative b, which is +1. There we go, +1 plus or minus the square root of plus or minus the square root of b squared, well, -1 squared is 1, minus 4 times 1 times -8, so that's like plus 4 times 8, right? All divided by 2a, which is 2. So I really get two answers there, plus and a minus. What did I solve for? Using the quadratic formula. X squared. It didn't solve for x, I solved for x squared, didn't I? Okay, so x squared equals one of two things. X squared could equal 1 plus the square root of 33 over 2, or x squared equals 1 minus the square root of 33 over 2, right? Okay, what's the next step? What would we do next? We solve for x squared, so what would we, this is going to look really ugly. I'm not going to give you any like this, by the way. But I just want to show you this would work. Square root, right? So ultimately, I'm just going to get x equals plus or minus the square root of all that stuff, or x equals plus or minus the square root of all that stuff. 4 solutions, right? Anybody see that? Okay. These are going to be real, aren't they? Because wouldn't you agree that this is a positive number? Okay. These are not. These are going to be imaginary, aren't they? Because 1 minus the square root of 33 is negative, isn't it? Anybody see that? So these would be imaginary. These would be real. Okay. I don't want to spend any more time on that. There's kind of a way we'd have to treat these to write them with eyes, but today's not the day for that. Okay. I just want to show this would work. Okay, factoring by grouping. So let's go back to factoring by grouping. Remember, that was our preferred technique for factoring, for solving quadratic trinomials where the factoring was more difficult, where a wasn't equal to 1. But it'll even work for a equals 1. How? How could I factor that by grouping? Remember, grouping I needed to be able to group, I had 2 groups, so I need to have an even number, so 2 groups of 2. I need to have a total of 4 terms in order to group this into 2 groups of 2. And that's essential. I need to be able to do 2 even groups of some number of terms. We're only going to do 4-term polynomials in here. But how could I split that up? If I factor that, what are my magic numbers? -10 and 4, right? And you got that because your magic numbers had to do two things, right? They had to multiply to -40 and, that's a bad star, they had to add to -6, right? And so we got the -10 and +4, right? Well, look at this. They add, the magic numbers add to -6. So how could I break this into 4 terms instead of, which term am I going to split to make 4 instead of 3? Hint, the magic numbers add to -6. What do you think? What do you think? Liliana, you have an idea? Say it again. -6 has to be split, doesn't it? Yeah, good. The -6 has to be split because that's the one that we know adds to my 2 magic numbers, right? So we end up with x squared, and then this is going to split into -10x plus 4x, right? I'm just splitting the -6, so I got it. The x goes with it. It gets distributed. -40, right? Okay, well now we can factor that thing by grouping. Remember what our steps were to factor by grouping. What's the first thing we did from the first group? A little review of this. First group of 2, what do I do? So you can remember, what did we do? Right, this is the one that we want to use instead of slip and slide. Remember, we always factored out the GCF of the first group. So what is the GCF of the first group? X. Okay, so there's my GCF. And then what's the binomial that's left behind if I factor out an x? Everybody see that, right? So there's the first group. And then we put our plus sign in the middle that separated the 2 groups. And what was the next step? If we can find magic numbers, which we did, you're guaranteed to be able to factor this by grouping. So how did we want to deal with group 2? Okay, I'm going to factor out a 4, but we're always going to start with the binomial because remember, the binomials need to be the common factors. So we know that if that's an x minus 10, without even thinking about it, I know that's x minus 10 because those are the ones I have to be able to undistribute in the next step. So what would I factor out to make that happen? What times x is 4x? 4, right? Okay. And now we get our answer. So if we factor out our common binomial factor, x minus 10, then what's left behind? X plus 4. There you go. Boom, we got it. Okay. Did we have to do that? No, we could have just jumped. I mean, that's way overkill. We could have just jumped right from there down to there, right? But factoring by grouping works. It's just not necessary there. Now, here it's more necessary, right? Because this isn't one we can just factor by inspection. This is a little tougher, right? So this time, remember what our magic numbers had to be. We had to know if they exist. If they don't exist, you can't factor this by grouping, or anyway, it just doesn't factor. So magic numbers here, magic numbers have to multiply to what? What do they have to multiply to here? 60, right? They got to multiply to AC. So that's the number they have to multiply to. and they have to add to b, which is negative 23. So there's the important part, right? What are my magic numbers that multiply to 60 and add to negative 23? Negative 20 and negative 3 are my magic numbers. And so we're just going to split that b term, right? We're going to split b into those numbers that add to b. Okay? So first two terms, what do they factor into? How do I factor in those first group? 5x, which leaves me what binomial? There you go. Okay. Plus, I know that's got to be my binomial factor. So what do I have to undistribute to make that happen? Negative, right? Which I could write as a negative 1 if I want to. Okay, so then now we got this thing factored, right? Now if we factor out our common factor, which is the binomial factor, what's left behind? Well, I could just divide each term by 3x minus 4, right, to see what's left behind. And what's left behind is a negative 1 there, isn't it, right? That's really a negative 1, right? So we end up with 5x plus negative 1 is 5x minus 1. We got it. Okay? Remember that stuff? That ringing a bell? Okay, why'd we review it? Well, because now we need it. Now we're factoring polynomials. It's not just an option like it was before. Now it's the only way to go, right? We have 4 terms here that cannot be combined. They're not like terms. So our only technique that we have at this point to try to factor a quartic polynomial that's got 4 terms. Actually, yeah, this is quartic. It wouldn't even have to be quartic, but a polynomial with 4 terms, okay, which would be, what do we call that? What do we call that? Who knows? 4-term polynomial. We don't care, right? What is it? Quartic tells us that it's a 4th degree, right? And this one happens to be 4th degree, but the fact that it's got 4 terms, I have no idea what you call that thing. You just call it a polynomial with 4 terms. So we're going to factor this by grouping just like before. So we could take out, what, an 8x cubed this time? Whoops. And then what's left behind if we do that? X, right, plus 9. Would agree? So how about this side then? We got to see, okay, so can we get an x plus 9 over here? We can. It works this time, doesn't it? I end up with a 1 there, and it works. And then I can finish this off if I factor out my common binomial. I'm left with x plus 9 times 8x cubed plus 1, agreed? And then this is really, look at this one, this is really just the quantity 2x cubed plus 1 cubed, right? I can treat this as a sum of cubes. And our final answer just ends up looking like x plus 9 times a plus, gosh, this thing isn't writing, a plus b times, times a squared, so quantity 2x squared is 4 times x squared minus ab plus b squared. There it is, right? Okay. Is it going to work here? Well, we'd have to just try it and see, wouldn't we? Right? So if we try this thing, I'm going to show you a way you don't have to just use trial and error. I'm going to show you a great trick. Here we would factor out a 5x squared, leaving us with x plus 2, right? So then we would need to have, if this is going to work, we would need to have the binomial left over here, x plus 2. Is there anything I can factor out to make that happen? It's not going to work, is it? Right? If I try to take out a 2, because I'd have to get a 2 there to get a 2x, but 2 times 2 is not 6. So that does not factor by grouping. It's not going to work. How can you tell? Look at the ratio of the two terms in each group. If the ratio of A over B is equal to C over D when we write it like this, so the ratio of the first two coefficients is equal to the ratio of the the last two coefficients, then it's going to factor by grouping, guaranteed. Guaranteed. How could you check that if they're weird numbers? Just look at the cross products. 72 equals 72, right? This other example that we looked at doesn't work. 5 over 10 is not the same as 2 over 6, so we know right away that one's not going to factor by grouping. Okay? Make sense? That ought to get you going. There's our test. And then I think I just had one more to go through as a practice. Here's what I'm going to do for you guys. I'm going to give you, Monday is going to be, we'll wrap this up, and then I'm going to give you a day to kind of finish up the 5.4 assignments and get questions answered and things. So just this one little example, and then the rest is work time. Wednesday, we'll look at some new stuff. Sound good? Okay, get your desks real quick. What's that? No, not the test won't be coming up for a little bit. I mean, you got probably a week before the test. All right. Have a good weekend. See you, Adelaide. Hold it. See ya. Hey, what's up?